In this video, we're going to talk about exponential growth and decay. If a population grows at a rate proportional to the current size of the population, then the population function satisfies the differential equation dB dt equals Kp. dB dt, that is the instantaneous rate of change of the population with respect to time. And the assumption is that that is proportional to the current size of the population. K here is a constant of proportionality. It's called the relative growth or decay rate. If it's positive, it represents growth, and if it's negative, it represents decay. If K is positive, then dP dt is equal to K times P. P is the size of a population, so that's necessarily positive, so K times P is positive. That means that the derivative, the instantaneous rate of change, is positive. And if the derivative is positive, that means the original function is growing. So it represents growth. On the other hand, if k is negative, then dP dt equals kp is negative. Again, p is necessarily positive, so if k is negative, then the product is negative. Kp, therefore, is negative. And since dP dt, the derivative, or the rate of change, is negative, the original function, p, is decreasing. If the original function is decreasing, that represents decay. This differential equation is one that we know how to solve. It is actually a separable differential equation. Let's go ahead and solve it now. Here we have it written as an example. It's phrased in terms of it's phrased as an initial value problem. The differential equation is here dP dt equals Kp. And here we have our initial condition. P of 0 equals P0. That is, P of 0 is the population after 0 time has passed. So P0 is the initial population size. What we really want to do is solve the differential equation, but notice that it is separable. dP dt is equal to k times dP. Not times dP, rather it's equal to k times p. P is a function of p, naturally, so this could be our g of p. And k is a constant, but you can think of that as our function of t. It's a constant function, so f of t is equal to k, and g of p is equal to p. However you look at it, this is a separable differential equation, so we can solve it using the technique that we've discussed before. dP dt equals k times p, divide the p over to the other side. And then we simply take the dt and write it over there. 1 over p dp is equal to k dt, and we integrate both sides. On the left, we have the natural logarithm of the absolute value of p, and on the right, we have k times t plus a constant of integration. On the left, we don't need the absolute value of p. P is a population size, so it necessarily has to be positive. So that means that the absolute value of p is simply p. So we have ln of p is equal to kt plus c. We exponentiate both sides. On the left, we have e to the ln of p. The e and the ln cancel, and we just have p. On the right, we do something that we did before. We write this as e to the kt times e to the c. These are two exponentials with the same base. So if you multiply them together, you add the exponents. This e to the c is an arbitrary constant, or at least an arbitrary positive constant. C is an arbitrary constant. It can be anything. So e to the c is any positive number. E to the c can't be negative, and it can't be 0, but it can be any positive number. So we can write this as e to the c times e to the kt, but it's very common to just replace this e to the c with some other letter, which we'll call a, where a is any positive constant. So we write that p is equal to a e to the kt. For any positive number a, this will be a solution to the differential equation. However, we have an initial condition. The initial condition is right here. P of 0 is equal to P sub 0. So if you plug in the initial condition here, P of 0 is A times e to the k0, but this is e to the 0, which is 1. So P of 0 is A, but P of 0 is what we were calling P sub 0. So what that means is that our solution is P of t equals P sub 0 times e to the kt. So the solution to the initial value problem is an exponential function, which is why we call it exponential growth, and it's e to the kt times the initial population. Let's look at an example. If a radioactive substance decays with relative decay rate k equals -3, how long does it take for 50 grams to decay to 25 grams? Here we're asking how long it takes for a substance to decay by half. That time is what's known as the half-life of the substance. What we have given to us is that the substance is decaying with exponential decay, and we're given a relative decay rate of k equals -3. That k, that constant of proportionality, is known as the relative decay rate when it's negative, and it's the relative growth rate when it's positive. So here we have a differential equation, dp dt is equal to -3 times p. And in this case, P of 0 is the initial population, which is 50 grams. We don't have to solve this differential equation because we already did it in the previous example. We know that P as a function of time is equal to the initial population times e to the k, which is a -3, times t. So this is our equation, or rather formula, or function that gives us population in terms of time. Now, our objective here is to determine how long it takes for the substance to decay from 50 grams to 25 grams. So our goal here is to find t so that P of t is equal to 25. Basically, our objective now is to solve for t. Because we know what P of t is, we've got the formula right there. So we have that 50 times e to the -3t is equal to 25. The first thing that you can do is divide everything by 50. Notice what happens. On the left, the 50s cancel, and on the right, you end up with 1/2. So you're looking for a t so that e to the -3t equals 1/2. Notice that there's actually no evidence here that you started with 50 and you're trying to end up with 25 grams. The only thing that matters is that it's half of the original amount. And in fact, it doesn't matter how much you start with. The half-life is the same. If you start with 50 grams or 100 grams or any other amount, the time that it takes to half that is always the same. So what is it actually going to be? Well, we know that e to the -3t is equal to 1/2, so we compute the logarithm of both sides, the natural logarithm. ln of e to the -3t is equal to ln of 1/2. ln of e to the -3t, again the ln and the e cancel because they're inverses, and you have -3t. What about on the right? Another way of writing ln of 1/2 is minus ln of 2, using the properties of the natural logarithm. So 3t is equal to ln of 2, so t is equal to ln of 2 over 3. And whatever number that ends up being, ln of 2 over 3, that's the half-life of this substance. As it happens, I did look this up earlier, or rather I computed it earlier, and this is approximately 0.231. So it's 0.231 units of time, whatever the time units happen to be. Let's look at another example. This is another example involving half-life. So if a substance has half-life of 30 years, find a formula for P of t, the amount of the substance after t years, if the initial amount of the substance is 100 grams. So what we know now is we know the half-life. We know what the formula is going to look like. It's P of t equals the initial amount times e to the minus kt. Or you could have just k and then use the fact that k is negative. But let's write it like this, where k is assumed to be positive. I know that this is decay, so I'm going to write it like this, where k is positive, but I have the negative sign there. What do we know about this? We know that the substance has a half-life of 30 years. So here t is measured in years. And we know that P of 30 is equal to half of the original amount, so 50. But we also know what P of 30 is in terms of the formula. It's 100 e to the minus 30k. And this, supposedly, is 50, because 30 is the half-life. So after 30 years, it decays by half. So now what we want to do is solve for k. Solve for k. So the first thing we do is divide by 100 on both sides. Then we have e to the minus 30k is equal to 1/2. Compute the logarithm of both sides. Whenever you want to get an exponent out of the exponent, and that's what we want to do here, k is in the exponent. In order to solve for it, we have to get it out of the exponent. So that means you're going to want to use a logarithm. Usually you want to use the natural logarithm, and fortunately, here we have ln of e, so those are inverses, so you just end up with minus 30k. And that's going to equal minus ln of 2. Again, ln of 1/2 is equal to ln of 2 to the negative 1, and using the powers of logarithms, that minus sign comes out, and it's minus ln of 2. That's supposed to be a 2 there. There we are. So what does this tell us? This tells us that k is equal to ln of 2 over 30. So that tells us what k is. What we want is we want the formula, so you just plug that back into here, just into where that k is. You plug that back in. So let's do that. So P of t is equal to 100 e to the minus ln of 2 over 30 times t. Now this is the answer, but you can actually do a little bit better than this, because you can simplify this expression. So P of t is 100 times e to the minus ln of 2, and I can write this as 1 over 30 times t. So let's just replace that as t over 30. Let me just fix that. Now I can also take this minus sign out. So I can take that out there. So we're going to have 100 times e to the ln of 2 to the minus t over 30. E to the ln of 2 is 2. So that tells me that P of t is equal to 100 times 2 to the minus t over 30. Or if you prefer, you could write this as 100 times 1/2 to the t over 30. And in this form, you can really see how the half-life works, because whenever t goes up to 30, or a multiple of 30, you get an extra 1/2 multiplied in there. And so that's why the half-life works the way that it does. The next thing we want to talk about is Newton's law of cooling. Or if you rephrase it, it could be Newton's law of heating. But let's phrase it in terms of Newton's law of cooling. So this law states that if an object is heated and then left to cool in a room, then the temperature of the object, which we can call capital T, after little t units of time satisfies the differential equation that you see here. The derivative of capital T with respect to little t is proportional to T minus Ts. Ts is the ambient temperature. That is the temperature of the surroundings, hence the little s that you see there. T minus Ts is the current temperature minus the temperature of the surroundings. So what this differential equation is telling you is that a heated object, when left to cool, will cool at a rate proportional to the difference between the temperature of the room and the temperature of the object. Let's look at an example. At 8 o'clock a.m., a cup of coffee having temperature 95 degrees Celsius is set down and subsequently forgotten in a 20 degrees Celsius room. When the coffee is 70 degrees Celsius, it is cooling at a rate of 1 degree Celsius per minute. At what time does this occur? So here we have a differential equation, and this may not look immediately like the same as the population growth, or in this case decay, but it's very similar, where here, instead of saying that the derivative of capital T is proportional to t itself, it's proportional to t minus a constant. In this particular case, the room has 20 degrees Celsius ambient temperature. So T sub s is equal to 20 degrees Celsius. We're not explicitly given what K is, but we can work it out. What do we know? We know that the cup of coffee starts off with 95 degrees as its temperature. So that means the initial temperature is 95 degrees. The other thing that we know is that when the coffee is 70 degrees Celsius, it is cooling at a rate of 1 degree Celsius per minute. So at the time t, let's call it t sub 0. At the time t sub 0, when the temperature at t sub 0 is equal to 70, we know, because the problem tells us, that the derivative of capital T with respect to little t, so this is happening at t equals t0, is equal to 1 degree Celsius per minute. So our objective here is to figure out what time this occurs at. So what we want to do is, our goal is to determine the value of t sub 0. That's our objective here. So we have a differential equation. dt by dt is equal to k times t minus 20. And we also have an initial condition. That initial condition is that t of 0 is equal to 95. So we can actually solve this differential equation in basically the same way that we've done before. This is a separable differential equation. So we divide by t minus 20, and that's going to equal k. And now we can just take that dt and put it up there. So we'll have 1 over t minus 20 d capital T is equal to k times d little t, and we integrate both sides. On the left side, we have the natural logarithm of the absolute value of t minus 20. And on the right, k is a constant, so this becomes k times t plus the constant of integration. Now what about that absolute value? T is the temperature of the coffee, which is warmer than the room. T is the coffee is cooling to the temperature of the room. That is to say, the temperature of the coffee is hotter, and it's slowly cooling down, getting closer and closer to the temperature of the room. In a limiting sense, we would expect the coffee to cool to room temperature, which is 20 degrees. So whatever function we end up with giving us t, if we solve for that t, what we would expect is that the limit as little t goes to infinity would be that capital T should equal 20. We'll see if that actually happens. But at any rate, we know that capital T is bigger than 20 because it starts off at 95 degrees and it's cooling. It's cooling down towards the temperature of the room, so it's certainly bigger. In particular, what that means is that capital T minus 20 in absolute value is just T minus 20, so we don't need the absolute value there. So this is ln of T minus 20 is equal to kt plus c. Now we exponentiate both sides, as we've done before. That's supposed to be an e. E to the ln of T minus 20 is equal to e to the kt plus c. The e and the ln cancel. So on the left you just end up with T minus 20. And this is equal to e to the kt times e to the c. Again, they have the same base, so when you multiply them together, that's the same as adding the exponents. So once again, we're going to write this as e to the c times e to the kt, and we're going to change this e to the c to a. C is an arbitrary constant, so a equals e to the c is an arbitrary positive constant. So the only thing that remains is to add that plus 20 to both sides. So we have t is equal to 20 plus a times e to the kt. So this is our solution to the differential equation. But at some point we need to remind ourselves that we have an initial condition here. And that initial condition is that t of 0 is equal to 95. So t of 0, this is t at little t. So t of 0 is 20 plus a times e to the k times 0. So even though we don't know what k is, that's fine because k times 0 is 0. So this is e to the 0, which of course is 1. So this is 20 plus a times 1. And this needs to equal 95. So that tells us that a is 75. So that tells us that the solution to our initial value problem is t of t is equal to 20 plus 75 times e to the kt. Now what we don't have yet is we don't have the value of k, and that's really what we need. Now where's that going to come from? That's actually going to come from our other piece of information. So we had another piece of information right here, and it said that at the time t0, when t at t0 is equal to 70, we know that the derivative is equal to 1. Okay, so the derivative at t equals t0 is equal to k times capital T minus ts. But what do we know about this? Well, for one thing, we know that t is being evaluated at t0. And we know what t at t0 is. T at t0 is 70. So this is 70. And Ts is the ambient temperature, which we also know. That's 20. That was our ambient temperature. And we also know that at this time, the derivative is 1. We know this just because we were told this. The derivative at the time t equals t0 is 1. That's what we were told here in the problem. Actually, that's not quite right. When the coffee is 70 degrees Celsius, it is cooling at a rate of 1 degree Celsius per minute. So actually, I forgot a minus sign here. This should be a -1 because it's cooling at a rate. So that means the temperature is decreasing. So if we go back down here, this should be a -1 there. If we didn't have a minus there, then we'd end up with a positive value for K. If K is positive, that means you actually have growth. Since the temperature is cooling, you have decay of temperature. Okay, now that we have this, we can write it out. -1 equals K times T, which is 70. Capital T is not always 70, just at this specific time. And at this specific time, the rate of change is -1. So it's 70 minus the ambient temperature, which is 20, which is K times 70 minus 20 is 50. So K is equal to a -1/50. And as you can see, there's a negative sign there. That's important for this to work. So now we just plug this value for K back into our equation there. And that will give us our equation for the temperature. So the temperature at time t, or t units of time after this is begun, is 20 plus 75 times e to the negative t/50. And this is our formula. That's our formula there. Let me just make the 75 look a little bit more like a 75. So now we found a formula for the temperature in degrees Celsius for t units of time after this mug has been abandoned or forgotten. Now what we're actually asked to find is not necessarily the temperature, but at what time is it that the coffee is 70 degrees Celsius? That's what we're actually being asked to find. But now we can do that, we can find that by simply setting this equation equal to 70 and solving for t. So to find t0, we use t at t0 equals 70 and solve for the unknown time, t0. Solve for t0. Because t at t0 we know is 20 plus 75 e to the negative t/50. But we also know that t at t0 is 70. So these two things must be the same. So that means that 20 plus 75 e to the minus t/50 is equal to 70. So subtract 20 from both sides. 75 e to the minus t/50 is equal to 50. And then divide by 75. That gives us e to the negative t/50 is equal to 50 over 75, which is 2/3. If you divide the top by 25, you get 2, and if you divide the bottom by 25, you get 3. Now what we need is we need to get that t0 out of the exponent. The way to get things out of an exponent is to use a logarithm. ln e to the minus t/50 equals ln of 2/3. The ln and e again cancel each other out, and you have minus t/50 equals ln of 2/3. So minus t0 is equal to 50 times ln of 2/3, and so t0 is equal to minus 50 times ln 2/3. This may seem paradoxical because there's a minus sign there, and t is the amount of time that's passed. So it looks like we have a negative time, but 2/3 is less than e. So ln of 2/3 is a negative number. What we need to do in order to answer the question is to actually evaluate this and see what time it is. t0 will tell us how much time has passed. and then we need to compare that to what time it is on the clock. If you compute this using a calculator or a computer, you should get that this is approximately 20.27. So your temperature of your coffee is 70 degrees Celsius, approximately 20.27 units of time after this has begun. So let's just remind ourselves what the units of time were. We started at 8 a.m. and then we forgot our coffee and it began to cool. What do we know here? We know that it's cooling at a rate of 1 degree Celsius per minute. So what that tells us is that we're measuring time in minutes. So that tells us that T0 is approximately 20.27 minutes. We started at 8 o'clock a.m. and by the time our coffee is 70 degrees Celsius, approximately 20 minutes has gone by. So at approximately 8:20 a.m., the coffee is 70 degrees Celsius. And that is the actual answer to the question.